All right, it looks like we're hitting 3 o'clock now, so wanted to welcome everybody to the webinar. Thank you all so much for being here. We're really excited to have Dr. Paul Markowski here today to talk to us about understanding and predicting tornadoes. So to help us with that chat, I'd like to introduce, before I get to the introductions, just one housekeeping thing. For any questions, we unfortunately will not be able to accommodate the raised hand feature today. So if you have any questions, please put them in the Q&A box and we will do our best to answer those throughout the presentation or at the end. So again, please use that Q&A box. I'll be monitoring the chat as well, but the Q&A box is really the place to put those questions. So to get us started, I'd like to introduce Erica Groh. She's one of our esteemed AMS Weather Band committee members, as well as an AMS certified broadcast meteorologist and a non-resident policy fellow for the AMS. She also works as a freelance broadcast meteorologist, among many other things. She's an amazing person. She's elected to the AMS Council in 2018 and is serving the final year of her term. She's also the chair of the AMS board on membership and previously served on several other AMS boards. So thank you for being here to moderate our chat today, Erica, and I'll hand it over to you.
Thank you, Tiernan. Happy to be here with you today. And I'm so excited for this discussion. If you've been seeing the posts on social media, you know that I've been looking forward to this for weeks. We are going to have a fantastic discussion. I already see a question in the chat, so I know that you guys are coming with great questions for us. So I'd like to introduce Paul Markowski, a distinguished professor of meteorology at Penn State University, also my alma mater. He was one of the organizers of the second verification of the origins of rotation in tornadoes experiment, shortened to Vortex-2, which you may have heard of. He's one of a handful of researchers who participated in both Vortex projects, by the way. He's been recognized for his tornado genesis research at the 2015 AMS Meisinger Award, the 2013 recipient of the NWA, that's National Weather Association's Fujita Award, and 2011 recipient of the European Severe Storm Laboratories DOTSEC Award. He served as chief editor of the AMS Journal of Weather and Forecasting from 2011 to 2016. So Paul, I know you have an introductory presentation that you'd like to give us. So please, without further ado, take it away.
Thanks for the really nice introduction, Erica. I'm really glad that the AMS is sponsoring these science talks, and I'm really happy to be invited to be a part of it. So I'll start with these images of what are known as supercell thunderstorms. These are the storms that produce virtually all strong tornadoes on Earth. They're probably the simplest way to define a supercell storm is a storm with a mesocyclone. So we're referring to rotation within the updraft of the storm. The updraft is where the air is rising. You can see it in this time-lapse imagery. In particular, the one on the left, you can really see the air rising pretty strongly, but it's also spinning as it rises. So the rotating part, the fancy term that meteorologists use is mesocyclone. And even though virtually all significant tornadoes come from these supercell storms, it's not the same as saying that all supercell storms make tornadoes. So more on that a little later on. But I would say, I guess meteorologists are pretty good at identifying these storms when we look at radar. That's the principal tool we use for warning the public about these storms. So what's shown here, this is what a meteorologist would see on a radar display. The term for this is reflectivity. So the radar transmits some signal, some of that's bounced back to the radar. Computer converts that signal into some useful, colorful image. So the red here is where there's really heavy rain falling. The yellow and green is where there's lighter or more moderate rain falling. And what a meteorologist sees that will get their attention is this, I guess we could call it an appendage on the southwest flank of this storm. This is called a hook echo because it's hook-shaped. The term echo is referring to the fact that the radar is sending the signal out, it listens for some signal to bounce back to the radar, much the same way if you use your voice to shout at a distant object. Some of the sound waves can bounce back. You can hear an echo. So these are microwaves. They're not sound waves, but that's where the term echo comes from. It's used somewhat casually by meteorologists. That hook-shaped echo is where the storm's rotation is kind of swirling the raindrops into this coiled structure. And if we look at what are known as Doppler velocities, so what's shown on the right here is what a meteorologist would call the Doppler velocity display. The radar in this case is located toward the bottom of the image. Where there are reds, these are winds blowing away from the radar, and greens can be inferred to be where winds are blowing toward the radar. So right in this region here, that's in the circle, we see a couplet where there's, in very close proximity to one another, winds blowing away from the radar and toward the radar, and the meteorologist infers that there's rotation there. So this is what the radar sees when it sees a mesocyclone. It's seeing this, it's a few miles across this area of counterclockwise rotation. The storm, by the way, there's a photo of it up here. I took this picture when I was living in Oklahoma years ago. And clearly, visually, we see that this is a supercell as well. It has this almost like an alien mothership in the sky appearance. This is the rotation that we can visualize really easily with our own eyes. So the radar is seeing the same thing, but in a different way. It sees that rotation in the storm. So supercells, I mentioned that these are the storms that produce the headline-making tornadoes on Earth. A strong updraft, so the part of the storm where air is rising, that's a really key ingredient to tornadoes. Well, it's also a really key ingredient to make big hail. So the biggest hail on Earth falls from supercell storms. In fact, I would say if you ever read the newspaper about 2-inch diameter hail or larger, you can pretty safely assume that a supercell thunderstorm was the responsible storm. And in fact, just yesterday, these are images, unfortunately, sent from my graduate school advisor on the west side of Norman, Oklahoma. He had damage to his own house. I hope this AMS talk didn't have something to do with it. I think it was just a coincidence. But yeah, he just texted me these images a few hours ago, and I thought, oh, good gosh, maybe I can use them later today. Are you okay with that? And he said, yeah, sure, no problem, Paul. But this was a supercell storm. So they don't all make tornadoes, but most of them make at least fairly decent size hail, and even the ones that don't make tornadoes, and some of them make absolutely gargantuan hail, like 4 or 5 inches diameter hail. So I'd contend that we actually know an awful lot about supercells and tornadoes. We routinely forecast tornado outbreaks in advance by hours, sometimes days in advance. It's really, really rare these days to have a high-end tornado occur without any warning. Now, false alarms are another story. I'll talk about that later. But I'd say overall, we have a pretty good idea of the conditions that you need in the atmosphere to get tornadoes. So what the rest of my presentation is about is all the things we know about these storms and how we use that knowledge to predict them. So how do we know what we know? So it's a combination of collecting observations in the field. So we put radars and other gizmos on trucks or small aircraft and take them to the storm to get a close look at the storm. The closer we can get, the more resolution we effectively have. We also use computer simulations because observations naturally have gaps in them. It's just not possible to observe everything that could be important at all times. So simulations actually run on a computer allow us to fill in a lot of the holes, although simulations have their drawbacks as well. Some things in simulations are necessarily approximated, and some of those approximations just frankly aren't so good. And then there's theory too. So just good old fashioned pencil, paper, physics, calculus. We can make a lot of headway, although we hit hurdles there as well. So all of these have their upsides and downsides. The bottom line is we can kind of view this as a three-legged stool: observations, theory, and computer simulations, when we use all three together, we have the best chance of making progress. So I'm going to take a little bit of a side trip here before diving right into tornadoes, just to talk about the fundamentals of how rotation in fluids in general intensifies. So vortices, that's just plural of the word vortex. A vortex, in simplest terms, is just a region of swirling fluid. So if we look at how vortices in general intensify, I would say that all vortices, period, whether they're in water or in the atmosphere or some other fluid, they intensify via what physicists call the conservation of angular momentum. This idea actually, by the way, goes back to the early 1300s, so it's a long time. It even predates Isaac Newton by a few hundred years, which is pretty amazing. So angular momentum, in simplest terms, it's just you take two quantities and multiply them together. So we'll call one of those V, which is a velocity. It's called here the tangential velocity. What that's referring to is just the speed at which something is spinning. All right, so that's the tangential velocity. You multiply that by what I'll call R, which is just a distance from wherever the axis of rotation is. So the products, or the result of these two things multiplied together, this is angular momentum. And this quantity V times R, when we say it's conserved, we mean that it stays the same approximately. Some can be lost to friction, for example, but let's sweep that under the rug for now. What it means is that if tangential velocity goes up, then the distance from the axis of rotation's got to go down so that the two multiplied together stays the same. So in plain English, the way a figure skater, we're all familiar with figure skating. Who doesn't like to watch figure skating during the Olympics, for example? Figure skater can increase his or her spin rate by taking their arms and drawing them inward. By drawing the arms inward, you're decreasing R, and by decreasing R, V has got to go up, so you spin faster. In the faucet or the bathtub, what's going on is fluids, it basically has an imperceptible rotation in it when you've got just a bathtub full of water. You might not have even, it might be basically still, but you get out of the tub or you introduce some disturbance. It's almost impossible to get out of a bathtub without disturbing the water a little bit. That disturbance gives the water just the slightest little torque. You pull the plug out, and as water approaches the drain, you're decreasing R, and the velocity V goes from something that's imperceivable to something very big because R is going very small. When you get to the drain, R is maybe just a millimeters as water's right at the center of the drain. So it's the same physics to describe two completely different processes: water draining out of a bathtub and a figure skater spinning faster. But these are both linked by the conservation of angular momentum. Well, the same thing happens in air. So here we've got a wildfire, and we've produced a wicked vortex. This is basically a tornado of fire. Here, instead of a figure skater drawing their arms inward, we've got a heat, hundreds of degrees. The flames are making air go up. And where the air goes up, air's also got to come together horizontally. And as that air comes together horizontally, it's just taking some existing spin that's essentially weak and imperceivable. But as R goes to something very small, V goes from something small to very big through this conservation of angular momentum. So you spin up a vortex. This is ingenious. Some of you know me and how much I like backyard campfires. Do not try this at home. These guys have set up a bunch of box fans around their fire pit. The box fans here are providing angular momentum. They're blowing air kind of in a circular fashion, but the flame is providing this intense updraft because it's hot air rises. And as the air goes up, it draws air from the fans inward, and the spin intensifies. They're making essentially their own personal firenado in the backyard. We can only dream, right? Here's an example where nobody's applied something as extreme as a fire, but these are what are known as dust devils. It's the same basic idea, just I guess less extreme than the fire pit example. Here, the atmosphere is naturally produced its own little hot pocket. The sun is shown on the ground surface. A pocket of ground has gotten a little hotter than surrounding areas. Air starts to rise there. I mean, the birds know this. On a hot, fair weather day, you can see hawks or other birds soaring on these things called thermals. The thermal can also bring angular momentum together, and in extreme cases, spin up what's known as a dust devil on an otherwise fair weather day. I mean, these are both days with mostly clear blue skies, white fair weather, what are called cumulus clouds, but you would not want to open your mouth or your eyes when one of these things goes by. It's not a life-threatening event, but certainly the most extreme dust devils can kick up winds of 40, 50 miles an hour and make for some fairly spectacular video. The hurricane, now we're kind of ratcheting up the ante in the atmosphere. So hurricane also gets its spin. Now this is a life-threatening vortex. Here, it's the same idea, but just on a bigger scale. This is thousands of times larger than the dust devil example. We've got spin, we've got air approaching the center of the hurricane. It's approaching the eye, and as it does so, it spins faster and faster and faster. So the maximum swirling wind, or the tangential wind, is very close to the hurricane. It's within what's known as the eye wall. So then we get to tornado. So here's some time lapse of a tornado. That's why everybody's here, because they're interested in tornadoes. This is actually a storm we collected data on in 2009 in Wyoming. It sounds like hyperbole, but this really is the best observed storm in the history of the Earth, which is kind of weird to say that, but it is. We had lots of radars on this storm, collected lots of other complementary data sets. But really the questions we want to ask ourselves is, where does the angular momentum come from? And what causes that angular momentum to be drawn inward to a small distance from the axis of rotation? Essentially, we're asking, why is the figure skater spin faster? We know why the figure skater does, but why is the tornado doing it? But the same basic questions. So for some clues, we're going to look at some ingredients in which we know tornadoes form. So here's some time lapse of a thunderstorm. You can see the updraft, the bubbly rising cloud elements. This is the updraft part of the storm. And if we launch a weather balloon just outside of the storm, so that ascends and it gives us a profile of temperature with height. That's what's shown over here on the left. So the blue line is what, say, some weather balloon might measure. I don't actually have a weather balloon set of measurements from this particular storm, but this is the basic idea. This is actually from a tornado outbreak day, for what it's worth. So one of the characteristics of tornado environments, and I would say even thunderstorm environments in general, is the temperature decreases fairly rapidly with increasing altitude. So this is what meteorologists refer to as instability. And if you force me to put numbers on this, I would say, if we're going to have a lot of what's called instability, we really need to have the temperature drop at least 25 degrees Celsius over the lowest 5 kilometers, roughly 15,000 feet of the atmosphere. What I've tried to do with this movie is match up the vertical scale of the cloud time lapse with the vertical scale of the temperature data that were collected by the weather balloon. All right, so then turns out what we can also compute is the temperature profile inside of a cloud. And we actually, we could launch a balloon inside the cloud as well, but it turns out we don't have to, because from some laws of physics and laws of chemistry, we can actually figure out the theoretical temperature inside the updraft. And in cases where we do have serendipitous observations from balloons or aircraft inside of thunderstorms, we actually know that our theoretical predictions are actually really, really good. They're good, certainly good enough to work with. So what's shown here on the left is now a red curve, which is the theoretical temperature inside of this thunderstorm's updraft. And if we compare that temperature with the temperature of the surroundings outside of the thunderstorm, where the updraft is warmer than the surroundings, we call that buoyancy. This is what's driving air upward. It's warmer than its surroundings. And the warmth that we get, the more warmth compared to the surroundings, the more instability we have. And this is ultimately a result of high humidity, particularly in the lowest part of the atmosphere. So I've said lowest kilometer, lowest, say 3,000 feet of the atmosphere. If you have a lot of humidity there, then this red curve is going to be increasingly to the right of the blue curve, meaning that it's warmer inside the updraft than in the surrounding atmosphere. So one other thing meteorologists like to do to quantify the total amount of warmth relative to the surroundings is we just look at the area between the red curve and the blue curve. So the bigger this area is, the more instability we have. And if you really want to impress your relatives at the next Thanksgiving dinner, you can tell them that this is all about convective available potential energy. CAPE is the fancy term or acronym meteorologists use for this. So CAPE has units of energy, which are joules, and it's measured for every kilogram of air that goes through a thunderstorm. A kilogram of air, if you're near the ground, it's about a cubic meter in size. So just think, a thunderstorm has lots of cubic meters of air going through it. If every cubic meter is releasing a few thousand joules of energy, you can do the math. There's a lot of zeros on the number of kilograms of air that go through a storm in an hour. You get tremendous energy release. It's actually far more than the worst nuclear weapons the human race has ever built. The key difference is a thunderstorm's bleeding out the energy release over an hour or several hours, whereas with nuclear weapons, the energy release is almost instantaneous. But integrated over a significant amount of time, the thunderstorm is going to be much more powerful than any nuclear weapon, which is why it's kind of futile to people. Maybe every 10 years or so, somebody jokes about using big bombs to disrupt hurricanes. That's like trying to stop a bus with a racquetball. It's just not going to happen. So rapid decrease of temperature with high humidity in the bottom of the atmosphere. These are two ingredients. And I'd say not just for tornadoes, but for any thunderstorms. And then a third key and part of the recipe is what's called wind shear. That's changes in wind with altitude. So if you look on this profile, which is, by the way, from a tornado outbreak day, and this is from weather balloon data, the winds increase very rapidly with height, and they also sometimes change direction rapidly with height. Both directional and speed changes with height are what we call wind shear. On big tornado days, you can have a 40-mile-per-hour wind speed difference over just a few thousand feet. I'd say at a minimum, you probably want 40, 50 miles an hour over the lowest 5 or 6 kilometers, 15,000, 18,000 feet or so. But without this wind shear, you might get thunderstorms, but you're probably not going to get significant tornadoes. All right, so how do the ingredients actually make a tornado? So here we can all put our storm chasing hats on. We're looking at this supercell storm. You can see the rotation in it. There's the mesocyclone. It looks like it's spinning. Well, it is spinning. This one in particular has a tornado beneath it as well. And there's wind shear in the environment. There's winds at the ground blowing kind of at our backs. If we're looking at the storm, maybe we're kind of looking to the northwest. So the winds at the surface are blowing from roughly the southeast toward the northwest. But winds above the ground are blowing out of the screen at you from, say, west to east. And that velocity or speed differential, this implies spin. And it's like football spin. In fact, the fancy word for this is streamwise vorticity, football-like spin. And instead of the storm sucking in lots of footballs, it's sucking in lots of blobs of air. Each blob of air it sucks in has this spin. And when you see this saucer spinning in the sky, what your eyes are seeing are the aggregate effects of thousands, millions of individual blobs of air, each taking its horizontal spin, and that spin becomes vertical spin when the air gets sucked upward through the thunderstorm's updraft. So we're going to graduate now from footballs to, these are called, we'll just call these things black arrows that show the axis of rotation. So the axis of rotation is horizontal away from the storm, that the red or magenta curved arrow gives the sense of spin. So it's kind of spinning like a rolling pin, right? So the storm sucks in this air, the axis of rotation gets reoriented into the vertical. But one issue here is that the rotation's only becoming vertical as it gets high above the ground. We're only getting vertical rotation up here. We're not getting vertical rotation right at the ground. So what we actually need is air to sink. And it turns out that if you look out here on the right side of this image, it's kind of fuzzy looking. This is rain that's falling. And where that rain falls, some of the rain evaporates and makes what's called a downdraft. That's just where air is sinking. So this air, it turns out, is flowing toward the storm as well, but it's getting rained into as it flows toward the storm. And as it gets rained into, it makes the air colder through evaporation. Evaporation chills the air. So the colder air sinks, and there's a temperature variation along this sinking air. You can imagine it's colder if you're looking into the screen where the evaporation's occurring in the rain area. Out where we're standing outside of the computer screen, we're out in the warm sunshine watching the storm as storm chasers. It's warm where we are. And where you have warm air and cold air side by side, that generates horizontal spin. It torques the air. So this is an angular momentum source. We asked the question before, where's angular momentum come from? Some of the angular momentum is already here. It's just in the ambient environment. But this angular momentum is only really contributing to rotation above the ground. But the angular momentum of the tornado, it's ultimately tied to this cold, warm spin. And what's going to happen here is that air that is torqued by this horizontal temperature variation, this air gets pulled toward the storm. It sinks as it's pulled toward the storm, and it also gets reoriented into the vertical as it passes under the storm. I mean, this is now basically, we're a large way, or this is a big step toward making a tornado. We're not quite there yet, but this is an important prerequisite to making a tornado. We now have angular momentum about a vertical axis of rotation, and it's right beneath the thunderstorm's updraft. So what we're going to do now, oh, I forgot this is in the pipeline. This is a movie showing where air is sinking. So the idea that there are downdrafts, this is not just a hypothetical or theoretical thing. We can see this in imagery. If you've ever watched a thunderstorm approach on a summer day, you've probably all experienced downdrafts, even in non-supercell thunderstorms, just garden variety storms. As the storm approaches, you feel the wind shift and the temperature drop. That is air that's been cooled by evaporation. So supercell thunderstorms have this as well, but they really exploit it in a way to generate angular momentum that can be ultimately used to make a tornado. All right, so now we're zoomed in. We're looking at, sometimes storm chasers call this the business district of the thunderstorm. So we're right underneath this updraft. Air is sinking out of the downdrafts and swirling around. And to make the tornado, all we got to do is further intensify this. This is now just where the figure skater comes in. Instead of having a figure skater draw their arms inward, we've got to make the air come inward. And the best way to make air come inward is to accelerate air upward. So it turns out if the air that's sinking is too cold, or that the suction from above is too weak, then what we get is just a weakly spinning vortex. It's not a tornado. It's maybe makes a swirl in the radar imagery, but it's otherwise sub-tornado strength. So this would be like the figure skater spinning around and not being able to draw their arms all the way inward. So they're not going to be able to spin as quickly. On the other hand, if the air that sinks through the downdraft is actually only slightly cooler than the environment, it's easy to lift that air back upward because it's not all that heavy. How heavy the air is related to how cold the air is, and how heavy the air is related to how easily it is to suck that air back up. And in sucking it up, that's what causes angular momentum to collapse to a small distance from the axis of rotation to spin the air faster. So if the air is not too cold or there's a lot of suction from above, then you get a tornado. So weak suction and cold air, no tornado. Strong suction and the air is only a little cold, you get a tornado. So we can see this when we look at time lapse of storms. Here we can see on the right, rain. That's a rain shaft falling out of the storm. Up here, this is the updraft. This is where air is rising. And you can really see with your own eyes air getting sucked out of the rain area and getting yanked or tugged upward. And in fact, right in here, at times you can see pretty strong rotation. In fact, there's a little funnel that forms in there briefly. So this storm didn't quite go all the way to making a tornado, but it got probably 98% of the way there before something else happened and short-circuited it. And this is one of the things researchers like myself are trying to better understand. What things help storms make tornadoes, but what processes can kind of short-circuit the process. So here's a case where it's a nice example, not because it doesn't make a tornado, although that's good for society, but this time lapse really nicely illustrates this ability of the storm to suck up some of its own cool air and convert horizontally oriented angular momentum into vertically oriented angular momentum. One pressing issue that scientists are, I'd say, still working on is some have hypothesized that there's also friction between the air flowing toward the storm and the ground. Here's the ground. And when an airstream comes close to a rough surface, that generates an additional vorticity source or source of spin. And some have thought that maybe this spin can also contribute to the tornado's rotation. I'd say that the jury is still out on that. In a way, it doesn't really matter because all tornadoes ultimately still need angular momentum. In a way, it doesn't matter where the angular momentum comes from as much as once there's angular momentum, what does the storm do with it? But anyway, this is what people are still working on. So I would say we're pretty good at forecasting when these ingredients come together, which is a good thing for society. This is why, as I mentioned before, forecasts are, I'd say, pretty good overall. For example, in this particular case, our NOAA's Storm Prediction Center, this is where the tornado watches, severe thunderstorm watches, other outlooks are produced. In the really big outbreaks, they sometimes give us 5, 6, 7 day lead time, which means that the computer simulations they're looking at actually days in advance are able to forecast when these tornado ingredients are likely to be present. I think this is a remarkable success of our field over the last few decades. Over here in the green box, I've just kind of summarized what those ingredients are again, but we've already talked about these: instability, strong wind shear, and then you need that for supercells. For tornadoes, you also want to have particularly strong wind shear right near the ground, and especially high relative humidity near the ground. That really helps that suction effect, and it prevents the air within the downdrafts from being excessively cold. But we're actually, I'd say overall, we're able to predict these ingredients pretty well. So you're probably wondering, why is tornado forecasting so difficult then? I'm making it sound like we know everything. Well, that's certainly not what I want to be conveying. So one of the issues is technological. If we look at this, this is just a schematic showing everything we've talked about, all the key processes that lead to tornado formation. Our satellites don't see any of this. The satellites are only seeing what's going on at the very top of the storm. So they're missing out on all this really interesting stuff near the ground. What's in yellow is what radars see. Radars can only see stuff where there's rain. So if there's no rain there, they can't see things. And I've also drawn here kind of near the ground, I've indicated that the radar can't see there either. And that's just because for the vast majority of thunderstorm events, the radar is several miles, tens of miles even from the storm, which, because the earth curves, the radar beam overshoots a lot of the key stuff right at the ground level. So we miss out on all of the interesting physics occurring along this downdraft. And then to top it off, the radar beam itself is kind of wide relative to small scale storm features. How wide this beam width is a function of how close the radar is to the storm, because the beam width has an angular size. It's about 1 degree wide. So 1 degree width, if you're only 100 feet from the storm, 1 degree is really small. But if you're 100 miles from a storm, 1 degree is going to be a few miles wide. So in general, the radar doesn't see the tornado, it only sees the mesocyclone. And therein lies the primary forecasting problem in the short range, is that radars are mesocyclone detectors, not tornado detectors in general. And not all mesocyclones make tornadoes. In fact, maybe as few as only 10% of supercells and their mesocyclones go on to make tornadoes. So there's, even though we're pretty good at identifying storms and environments that can support tornadoes, false alarms are a huge problem, because so many storms look like they check off all of the boxes, but something goes on to prevent the tornado from forming. In addition to technological limitations, there are still some pretty basic science questions. Storms look really similar in radar sometimes. Here are 4 different storms seen by a radar in their reflectivity appearance. They all have hook echoes. The mesocyclones are where the white circular arrows are. But only one of these is actually making a tornado. The other 3 are not. If you're a forecaster charged with issuing warnings, you probably warn on all 4 of these, and that would give you a 75% false alarm rate, which is actually about where we're at nationwide right now. You might be saying, well, you got to look at the Doppler velocities too. You can't just look at reflectivity. After all, we have this Doppler radar network. Well, here's a Doppler image. This is actually from just last Friday down in Texas. We've got one of these couplets where winds are blowing toward and away from the radar in close proximity. There's the rotation. This storm, in fact, made a tornado. Okay, what about this storm? This is actually from Tuesday in Texas. This storm has a really fantastic looking hook echo. Look at the swirl here in the reflectivity image. But the mesocyclone is extremely intense. And in fact, if we look at winds toward or away from the radar here is up toward the upper right. There's just a hellaciously strong mesocyclone in this storm. But one of my former students was on this storm. This did not make a tornado. Another key issue is that some storms just have really unremarkable radar presentations. These aren't even supercells. And for example, in this case here, this little velocity signature made a tornado. Good luck issuing warnings for that sort of event. So for more marginal forms of storms, we still have a lot of work ahead of ourselves. And what I'll do kind of to wrap things up is talk about predictability challenges. So in addition to technology and basic science issues, even if you have perfect technology and a perfect understanding of the basic science, this still doesn't guarantee we can predict things well. And that's because of what's sometimes known as chaos. Many of you saw the film Jurassic Park, where the actor Jeff Goldblum, is that his name, was flirting with the scientist and talking about chaos theory. And here we have that same principle in the atmosphere. Here are 25 computer simulations of a would-be tornado-making storm. These all have hook echoes. The white little streaks are tornado swaths. It's almost random what the behaviors of these storms were, but these storms are all in virtually identical environments. The only thing that's different is essentially where just little thermals are placed. But on average, these environments have identical wind shear, identical instability. And that goes to show that I think for some time, we're going to have challenges ahead of us. So kind of the direction the Weather Service is going now is to migrate tornado warnings toward what are known as probabilistic tornado warnings. So instead of just being told you're in a tornado warning, you're not in a tornado warning, I think there's going to be a trend in future years to talk about probabilities and update those probabilities on a minute-by-minute basis. So the moderators are telling me we need to move to the Q&A session. So I'm actually going to stop sharing my screen and I'll let Erica take over from here.
Well, you'll be doing most of the talking still, Paul, but I wanted to share some of the excellent questions that have been coming in from the audience. Now, the first question here, this is an anonymous attendee, and you already walked us through the tornado genesis, but he's asking about whether the rotating wall cloud forms in the forward flank downdraft, or is it in the rear flank downdraft? And I think that most of them are RFDs, and then forward flank, those are like more commonly the little weak gust NATOs. Is that correct?
Yeah, so that wall cloud is where air coming out of the forward flank is getting sucked upward. Mm-hmm. But the wall cloud itself is kind of at the it's on the cool side of where the interface between ambient warm humid air is and the rain cooled air. But it's kind of where there's an intersection between forward flank and rear flank downdrafts. And that's certainly, if there's going to be a tornado, this is where the action is going to happen.
Mm-hmm. It's the interface, yeah. Okay, thank you. Philip Caldwell wants to know if there's ongoing research investigating the application of infrasonic for the detection and location of tornadoes. He also asked about LIDAR. Would they offer any advantage over the Doppler radars that we use today?
Yeah, so that's a great question. So let me start with the LIDAR. That is an easier answer. So one limitation of LIDAR is that it can't penetrate rain. So as soon as it hits an intervening raindrop, that's it. So anything that's embedded in rain is going to be invisible to a LIDAR. As far as infrasound goes, one issue is I'd say the jury is still out on the link between infrasound and tornadoes. There's certainly a camp that believes there's a connection between infrasound generation and vortices, but frankly, it's still a mystery as to if the tornado is generating the infrasound, what exactly is physically making the infrasound. But even if there is a smoking gun link, and I'll say that the smoking gun has not yet been identified, but even if there is one limitation of infrasound is sound just travels so slowly relative to the speed of light. So you would need a lot of infrasound detectors to have any utility. Sound only travels a mile in 5 seconds. So if a tornado is only going to last a minute, if your sensor is just 10 miles from the storm, you're basically only hearing the infrasound as the tornado is dying. So you need a whole lot of detectors all over the countryside if you're actually hoping to detect tornadoes via infrasound on a timely basis.
So forgive me, I'm going to take moderator's privilege here to ask an intervening question here that's very related. Is our Doppler network as it currently stands in the CONUS substantial enough to catch most severe weather? I know we're not going to catch all. And if it's not, what is the most radar sparse area that desperately needs more 88Ds?
Ooh, that's a good question, Erica. So as a scientist, I'm naturally drawn to data. So if you ask a scientist if you need more radars, the answer is yes. Yeah, I would love.
Yes, it doesn't matter what.
So,
yeah.
Right. So first off, we have the best Doppler radar network on Earth. Period. There's really no comparison. It's reliable. It's there when we need it. Having said that, there are parts of the country where there are some gaps, and those could be alleviated by putting radars in the gaps. We might call these loosely gap filling radars. They basically just give us better coverage, especially what more radars gives you is better coverage down low in the atmosphere, and also higher resolution, because if you have more radars, it means the average event's going to be closer in proximity to a radar, which means you see it better. So the Western US has some holes, especially in the mountainous areas where mountains block the radar beam. You might have an entire sector of the sky that is essentially invisible to the radar. Not as many people live in those areas, which would probably be the argument that an administrator would give for the trade-off that's been made. In the eastern US, I work in Pennsylvania. In southeastern Pennsylvania, we have a notorious radar hole in the Harrisburg area where the nearest radar is 100 miles away. And there's quite a few people that live there. So yeah, I'd probably want more time to go on a map. I'd probably pull out my paper and pencil and circle some areas, put radars here, 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 and here. But the short answer is, yeah, we could do better with more radars.
Okay. The next question from Rick Halterman, and someone did answer this in the chat, but I wanted to give you an opportunity to share because we do have hundreds of people in the audience talking about the Coriolis parameter, which is generally applicable to larger scale weather phenomena. But his question is, does it have any influence on tornado genesis?
So the short answer is yes, but it's indirect. So the vast majority of tornadoes in the northern hemisphere spin counterclockwise, and in the southern hemisphere clockwise. It's probably 99% spin that way. So that can't, given that huge preference, it can't just be random. So the Earth, that just reeks of, okay, Earth's rotation's got to be having some influence. But the way that it has an influence is actually rather indirect and requires some somewhat high-level meteorology courses. It essentially has to do with the fact that the vertical change in wind speed and direction, the so-called wind shear in the atmosphere, the characteristics of the wind shear that favor ultimately counterclockwise rotating tornadoes in the northern hemisphere. So there's this whole chain of events that occurs, which I stepped you through in those schematics, where there's horizontal spin that becomes vertical, then you've got downdrafts. All that stuff is happening in an environment that has a wind profile that ultimately gives preference to counterclockwise rotating tornadoes. And that's how the Coriolis has an impact. So it's quite indirect. By the time you get to the final spin up of the tornado through we'll call it just loosely, the figure skater effect. You've got angular momentum, you just now need the final step of bringing it together to produce tornado strength spin. At that point, the Coriolis force is irrelevant.
A question from David Katz, who worked on a field experiment in the early 70s in Oklahoma where they released radiosondes into the environment between storm cells, eventually getting drawn up into the updrafts so they couldn't make measurements of the ambient environment, he says. Have you seen this in other observational studies, he wants to know.
Oh, I'm sorry, Erica, have we seen what exactly?
Oh, he says that the radiosonde balloons were released into the environment between storm cells, but they eventually got drawn into the updraft, so they couldn't make measurements of the ambient environment.
Oh, yeah, I mean, that sometimes happens to our balloons. The fancy term for that is they get
Is it a problem? Is it consequential?
Well, it depends on what you're trying to measure. So yeah, if you're trying to measure the environment, then you don't want the balloon to go into the storm. So yeah, we launched so many balloons in field projects. I'll just say some are winners and some are losers. And sometimes in real time, you don't know which ones are going to be optimal. So you just launch a whole bunch. And then after the fact, it takes, when you watch movies about scientists, they're always doing the analysis in real time. You know, they haven't even gone for dinner yet after the storm chase. They're like, oh yeah, we got a great data set. We now found the missing link. Real life, it's 5 to 10 years of analysis. Nobody'd stay in the movie theater that long.
Another question from Rick Halterman, which is very similar to one of the questions that we discussed yesterday. Are the mechanisms for tornado formation the same in weak non-supercell tornadoes, such as in QLCSs, which is quasi-linear convective systems for those who have not yet heard that term? The question that I had posed to you yesterday was, why out in the Midwest and the plains is it so much more common to get those supercells? I think in my entire career in the Northeast and Mid-Atlantic, I have not seen what I would consider a classic supercell in my entire career. But those QLCSs, oh yeah, we get them.
Yeah.
You know, it's not hard at all. And those, by the way, are relatively shallow They're closer to the ground. They don't have as much going on in the vertical as the supercell tornadoes that you get out in the plains and Midwest.
Yeah, so these are great questions. In fact, they're going to be on my exam at Penn State next week. So I hope nobody from my class is
right. Yeah,
dropping on this. Gosh, that was like a 5-part question. I guess the first question is about mechanisms being different in squall lines. The short answer is, yeah, probably. I mean, fundamentally, the angular momentum conservation part, the last step where you've got some sort of angular momentum, you've got to contract it to a small radius to make a tornado. That's going to be constant across all storms and all fluid. I mean, that's just a basic process in fluids to make a strong vortex. But in different types of storms, the source of angular momentum might be a little different, or it might not be, but maybe the mechanism that makes it go from horizontal to vertical angular momentum is a little different. One thing that's going to be constant, though, across all types of storms is that to get vertically oriented angular momentum at the ground, it's either got to be there before the storm gets there, or if the storm only has horizontally oriented angular momentum, it had better have downdrafts to bring it to the ground, because if only updrafts make it go from horizontal to vertical, the air is rising away from the ground. We've tried in simulations to make tornadoes this way. It just doesn't work without the downdraft. So downdraft, it could be that in squall lines, downdrafts are still key. It's just a different structure than the supercells. Strangely enough, I'd say we probably know more about how intense vortices form in supercells. They're easier to study for a number of reasons. And it's the forecasting tornadoes and squall lines, the signatures are often really unremarkable on radar. It's a good thing that in general, these are not the most violent tornadoes. Having said that, I'm not going to say that we should blow off a tornado warning that's associated with a squall line, but I think this has been studied. 98 or 99% of tornado fatalities are in supercell tornadoes. So fortunately, the ones we know the least about, which is the ones not in supercells, those are fortunately not the most deadly ones. So they're not as societally critical. And then Erica asked a question about plains versus Northeast or something along those lines. Of course, the physics is agnostic about where you're at. If you know, the same equations that apply to Oklahoma apply to Georgia and they apply to Pennsylvania. It's just that what climatology is how frequent those particular conditions occur in one place or another. So if you get a Pennsylvania atmosphere in Oklahoma, you'll get a Pennsylvania storm in Oklahoma. On the other hand, if you get an Oklahoma environment in Pennsylvania, you're going to get an Oklahoma tornado event in Pennsylvania. It just doesn't happen much in Pennsylvania. And one of the reasons why the Great Plains is so special, and if you look at a global map of tornado, we'll call it tornado friendly environments or tornado capable environments, the Great Plains of the US stick out like a sore thumb. This really is a unique spot worldwide. There are other hotspots. East of the Andes Mountains, southern Brazil, parts of Argentina, Bangladesh, southeast of the Himalayas, north of the Bay of Bengal, parts of Southeast China, north of the South China Sea, downwind of the high altitude Tibet Plateau. What all of these areas have in common is they are poleward. So by poleward, we mean in the northern hemisphere, north of, in the southern hemisphere would be south of, so in the direction of the pole. Places that are poleward of really warm bodies of water and east of major mountain barriers. So Tornado Alley is poleward of the Gulf of Mexico, downwind of the Rocky Mountains. And the Gulf of Mexico is the warmest body of water in the world at its latitude. So it's a tremendous moisture source. The moisture is one of those key ingredients for developing instability or CAPE. So in Argentina, you've got the Andes Mountains, and actually in Argentina, it's probably the Amazon rainforest that ends up being the moisture source north of the hotspots in Argentina. Anyway, that's a an abridged version of the answer to your question. Good
No,
question.
I think, Paul, it's great that you walked through what we would call a synoptic scale, explanation as to why the Great Plains is really the unofficial tornado capital of the world. This question is a very loaded question from Bob Robbins. Do people get annoyed that so many tornado warnings are false alarms? I would argue that that's outside of your purview, and that's more that's more in mine.
Yeah, I've got a lot to say on that. That's a good
Feel
question.
free.
Can I answer
Yeah,
that?
of course. Yes,
So,
please.
so first off, as I mentioned, it varies a little bit year to year, but overall, a good round number is about 75% of tornado warnings are technically false alarms.
Mhm.
As to whether this is a problem or not, so let's call this the crying wolf syndrome. If you're warned repeatedly, you become desensitized, you might be reluctant or slow to take action on the 20th time you're warned. It's like loosely pulling the football on somebody. But so first off, we've got actually a lot of social scientists studying this problem now.
Mhm.
And one thing they're finding is that actually meteorologists have always assumed that false alarms have a real detrimental effect on response of the public. Social scientists are actually finding that meteorologists probably overestimate the negative aspects of over warnings and false alarms. If false alarms aren't as detrimental as meteorologists maybe think they are, so this would argue for being more aggressive on issuing warnings. What I would add to that is that not all false alarms are created equal. So the way the National Weather Service counts false alarms is certainly easy to apply from just a bean counting perspective. What ends up happening is Weather Service puts out a warning, and it's in what's called a polygon, that they'll draw a box, and that's the warning area. And if the event or tornado happens anywhere in the box, it's a hit. If it doesn't happen in the box, it's a miss. It's a false alarm. But the problem's a lot more complicated than that. So for example, if you're in a warning and you step outside and the sky is black, the rain is blowing horizontally, you look up and you see this spinning around and there's no tornado, that's a false alarm. But that's a very different false alarm than if you get buzzed for a tornado warning, you step outside and you look up and you see blue sky or nothing that's really threatening. So in the first case, both of those are false alarms, but in the first case, you perceived a threat. That horizontal rain and black sky and swirling clouds, that scared the heck out of you. The next time a warning is going to be issued, I bet you're going to respond, because you're going to be like, well, last time I was glad I got a warning. That was a really scary storm. In the second case, where the person saw blue sky, the next time there's a warning issued, the first thing they're going to probably do is go outside and say, all right, are these clowns, issuing another warning? What's going on here? So you're going to be slower to respond if you don't outright dismiss it. So there's a whole gray area of good warnings and bad warnings, or good false alarms and bad false alarms. I would say that a good warning is any warning that's issued when there's a credible threat from a storm. And whether the event happens or not shouldn't dictate whether that warning was a good warning or a bad warning. So if a trained meteorologist sees a signature on radar and says, that's a threatening signature, I think there should be a warning, period. And that's a good warning. And if the event doesn't happen, so what? I think scoring that as a false alarm maybe isn't the best service overall for the public, because I think we just have to explain to the public better that there's certain limits to predictability. We are not going to be able to predict any time in the near future, and probably not ever. We're not going to be able to say, okay, 26 minutes from now, a tornado is going to form 100 yards from your house. It's going to be EF3 in strength. It'll last 4 minutes. And 29 minutes from now, this storm is not going to make a strong tornado, but it'll make a weak tornado. We're never going to have that level of specificity, which gets into the predictability challenge I mentioned before. I mean, maybe a more familiar example to you is little white puffy clouds on a fair weather day. I can't tell you if the next puffy white cloud is going to form over my house or over the house in the next neighborhood over. just because I can't do that doesn't mean that I have no idea how white puffy clouds form. I know how white puffy clouds form, but that knowledge doesn't translate to predictability. I can't tell you where the next white puffy cloud is going to form. And I think we're kind of in that same predicament with tornadoes. Unfortunately, tornadoes can be deadly and white puffy clouds are not.
It would be like putting a pot of water on the stove and trying to predict where those first bubbles are going to start to,
Exactly. Yep.
Yeah. So Paul, we are at 4 p.m. I wanted to get the question from our undergraduate meteorology major who is on here. And then I believe, Tiernan, if you can confirm for me that we have made a Q&A available for people whose questions we did not get to today. But while you're, getting that ready to wish everybody farewell and have a great day. This question is from Jordan Tweedy, who says that they still have a lot to learn. So what kind of research projects are most needed to better predict tornadoes, and what can students do to help?
Oh, that's a great question. So,
Good one to end on, right?
yeah. So one thing we have I would say in our field projects, we have a huge surplus of mobile Doppler radar observations. You've seen some of these on TV. Doppler on wheels radar. There's these smart radars as well. Some other schools have radars too. But what radars give you are winds, and we know where there's a tornado. We even know maybe how the winds have evolved to make a tornado. But in science, we're trying to understand the physics behind why the wind is swirling the way it is. And if you're trying to understand how the tornado got there, you need to know the forces. So the radars don't give you the forces. They only tell you what's happening. If you want to know why that's happening, you need to measure pressure and pressure gradients, because that's what accelerates air. You need to measure buoyancy, so you need to know something about temperature. You need to know where rain is and how it's contributing to sinking air. And the radars don't measure those things. So what we really need are, it's kind of like the movie Twister, where they had all it was Dorothy, right? The fictitious device that had all these little balls fly around. We need something actually bigger in scale. We need to be able to measure temperature and pressure in a few cubic miles surrounding a developing tornado. Radars don't do that. And there are teams working on this. Some are using drones. My group at Penn State, we're launching small balloon-borne probes. The balloons are only this big. We can throw them out the window, and they carry temperature sensors and pressure sensors with them, and GPS as well. We can track hundreds of these simultaneously now, which is actually a non-trivial electrical engineering feat. But those are gory details. I'll hand it back to you.
Thank you so much, Paul. And Tiernan did post in the chat to let everybody know that the conversation will continue in the AMS Weather Band community. So you go to amsweatherband.org and click on the community forum. And if your question was not answered today, you'll have an opportunity to ask Paul in that forum. And to everyone else, thank you so much to the hundreds of participants and a couple dozen people who asked just outstanding questions today. I thank you very much. And Paul, thank you so much for giving us a really in the weeds, in-depth look at how tornadoes form.
Thank you. Thanks, Erica.
Have a great day, everybody.